Hi, I'm Laren. This is Knife Steel Nerds. I've got another Q&A video for you. We've got a bunch of interesting questions from my Patreon supporters. Thank you, Patreon supporters, for sending in all of your questions. We've got some really interesting ones. This first one is quite complicated, so we're going to get right into it. A lot of metallurgy to cover in here. So he says, I saw some research articles recently on ultra-high toughness in ferrite/martensite laminated steels. The average Sharpie impact value was around 400 joules, 295 foot-pounds, with a tensile strength around 1 gigapascal. Could the high toughness/high strength combination of these materials possibly carry over into a new knife steel? Here is a link to one of the articles published in Nature. Okay, so I pulled up this article, and this is the laminated ferrite/martensite microstructure that he's talking about. So in knives, we are familiar with laminated steels and Damascus, but this is not laminating two different steels together. The laminated microstructure it's talking about is within a single steel. So through specific alloying and processing, they hot rolled the steel where it had both phases, ferrite and austenite. And when they quenched the austenite, it formed hard martensite. So this is a mixture of soft ferrite and hard martensite. And it looks laminated because it was formed during hot rolling, so everything is elongated. So that's the first thing to mention. And then when they break across those layers, it seems to break, so they break it so that it goes through the layers, and then that leads to this fracture that has to cross through the soft phases, and that leads to higher impact energy. Now, this is actually something I almost covered in one of my Damascus videos, because they have done studies on this where they've taken high carbon steel and low carbon steel and laminated it together and then broken them across the layers, and it does lead to higher toughness. Now, this doesn't always lead to a benefit. So I talked about this in the Damascus video, where with typical Damascus construction, we don't break through the layers. So when we take a laminated piece of steel, all of the layers are going in this direction. And then when we have an edge of a knife like this, here's our knife edge alongside our bar of steel. And then when we're chopping, let's say the crack has to grow this direction. So not through layers, but through all of the layers, we'll say. And when I tested toughness of these steels, having a tough steel mixed in with a harder or more wear-resistant steel, it did not increase the toughness. So the orientation matters a lot, and most Damascus or laminated constructions are not leading to higher toughness. So that's one aspect. Maybe you can play around with orientations and get some interesting properties, but with most laminated steel, including the orientations they're talking about through hot rolling in this paper, would not benefit edge toughness. It might benefit when you are flexing an entire blade. So let's say we have a Sanmai blade and you have to break through those layers, or just Damascus in general. So that's sort of interesting, but breaking a whole blade I think is not quite as important as our edge toughness in general, but there are some interesting aspects there. The other thing he mentioned was the strength-toughness balance, which in this paper is right here. So we've got ultimate tensile strength on our x-axis. That is highly correlated with hardness. And then on our y-axis is the Sharpie impact energy. And the new steels that they looked at are in this range, as high as about 1,500 megapascals. They also had one that was around 1,700, 1,800 megapascals from a reference paper. I'm not sure what that one is. And then when you've got steels that are in the 2,000 megapascal range, they are quite low in toughness compared to softer steels. So I came up with a simple conversion chart. This is just using values from standard charts. I didn't create whole new values for this, so they're going to be a little off, but they can represent what we're looking for. So if we look at 60 Rockwell C, that's about 2,200 megapascals tensile strength. So when we're looking at 1,500 megapascal tensile strength, we're in the mid 40s, maybe high 40s. So with the type of strength level that it's talking about, it's not exactly desirable for a knife, where we typically want to be above 55 Rockwell C. Also, if we have a mixture of soft and hard phases along the edge, that is usually undesirable, because soft phases mean that we can get edge deformation. When you're just pulling a tensile bar until it breaks, the overall strength of the material is what matters. But when we're looking at an edge on a microscopic level, we need the whole edge to be strong and hard so that it resists deformation and stays sharp. So I think there are some interesting things in that paper. There are things to learn, I think, but would we want to mimic exactly what they did in that paper? The answer is no. Okay, next question from Delta Sheath. I'm getting 80 CRV2 from NJSB, that's New Jersey Steel Baron. I have an even heat furnace for heat treat. After seeing your video on 80 CRV2, I'm left wondering if I should normalize and anneal my as-received 80 CRV2, even though I am not forging, in order to reach the fine spheroidized microstructure and thus increase the final hardness of my 80 CRV2. Okay. So 80 CRV2 is a relatively simple steel. It's got 0.8 carbon, it's got 0.5 chromium, 0.2 vanadium. So it is a common steel for forging bladesmiths. However, some stock removal makers do use it. And he's saying, should he go through some type of normalizing process with his steel? So this is the structure of the New Jersey Steel Baron material. It's made by Buderus in Europe. And you can see that it has relatively coarse carbides. Then Alpha Knife Supply and Jantz, they sell material with more of a medium coarse microstructure, and it responds a bit differently to heat treating. And this is the microstructure from my recommended thermal cycling when you're forging it. So you can see the carbide structure is much finer. And then New Jersey Steel Baron themselves also have a data sheet with a certain cycling procedure that I don't really recommend because it mostly results in perlite, and I prefer spheroidized carbides. But this also changes how the steel heat treats and the resulting hardness and toughness. So here is hardness versus austenitizing temperature for a 10 to 15 minute austenitize before quenching. So this is the Buderus material from New Jersey Steel Baron. You can see if you use 1525 as quenched, you'll get 62.5. Versus my recommended cycling where you would get 66 Rockwell as quenched. And to get that type of hardness with the Buderus material, you'd have to be up into the 1650 range, which is pretty hot for this type of steel. When you start with perlite, it can get even harder. Perlite, you don't have much control over your hardness. You can see when it has a fine spheroidized microstructure, you can get different hardness levels depending on the austenitizing temperature you choose. For perlite, even with 1475, it was already maxed out in hardness, and it can be difficult to get these nice curves where you can control your final hardness. Another reason why I don't generally recommend perlitic starting microstructures. But this can also affect the toughness. So here is my cycling using 1525 400 degree temper. You get 30 foot-pounds in my test and 61.5 Rockwell or so. Where if you start with the Buderus material with the same heat treatment, you get only 58 Rockwell, and the toughness is no better, even though it's significantly softer. So you would have to austenitize hotter or temper lower to get the same hardness. And maybe the toughness goes down at that point. So should you thermal cycle the steel to get something more like this than like this? It's totally up to you. I mean, these properties aren't terrible. It's a little soft. You can compensate with the heat treatment, but then the toughness may go down some. However, you do get a bit more carbide. You can see these little white particles. There are more carbides in this material than when you use my cycling, where the carbides are much smaller and there's a smaller volume of them. So you might get a bit better edge retention, though your toughness hardness balance is a bit reduced, and you're going to have to heat treat the steel hotter to get similar hardness. So it definitely doesn't hurt to go through the type of cycling that I recommend in this article to get the fine spheroidized structure. You can get a little bit higher hardness toughness balance. But, you know, our customer is going to tell the difference. That is always hard to say. You know, it's not like this Buderus material following a generic heat treatment is bad or terrible. But could it be optimized more? Probably. Okay, next question. Roughly how much forging or annealing does it take to eliminate the as-rolled stretched out carbides in a blank? So what he's talking about is this type of microstructure. So the steel, as it comes from the factory, has been hot rolled out to a much smaller dimension than the original ingot, and that leads to elongated features. So manganese sulfides, all steel has at least a little bit of sulfur in it that combines with manganese, and it forms these particles called manganese sulfides, and they are soft at forging temperature, and so they elongate during hot rolling. Now, knife steels also usually have a lot of carbide, and the carbide also gets elongated and you get these stringers, they are called. And that leads to worse toughness in this direction. So when you're breaking across these carbides or across these sulfides, it reduces your toughness. So if these were perfectly isotropic, meaning they were not elongated in one direction or another, your toughness would be the same regardless of direction. Now, can you eliminate that by forging a knife? No, not with a small amount of material. What you'd have to do is called upset forging, where you would forge in the opposite direction of the rolling direction. So you'd have to like turn a bar vertical in a forging press and then forge it down. But, you know, you almost always have to elongate steel, and upset forging doesn't eliminate all of this segregation, but it can help. There are some papers on this, but it's a difficult process. How much you would have to do would depend on the steel and how much of these elongated stringers you have or manganese sulfides. I don't think there's a realistic way to get rid of them. This is what processing like powder metallurgy is for. It helps reduce the amount of segregation that occurs, and you get less directionality in the toughness. All right, from Brian Bailey, is there any hope for CruForgeV coming back into production, or is it dead forever? Well, CruForgeV I have written about before. So it came out in like the mid-late 2000s. It was a steel that was designed for forging that would have some vanadium addition, so 0.75%, to have some wear resistance, because most steels used by forging bladesmiths are pretty low in wear resistance. And the steel, okay, it came out in 2009. They made 40,000 pounds of it, but Crucible went through a bankruptcy shortly after, and they basically offloaded all of this steel. More of it is still out there that you can buy, and it sells pretty slowly. And when I have brought up CruForgeV with Crucible people, they have never mentioned any interest in making the steel. The response to the new steel was pretty muted. To this day, it's not that popular. So if you ask me, I think it's dead. I don't think it's coming back. Now, it's not patented or anything. Maybe another company could decide to make it, but I don't see it coming back. I don't think so. Okay, the next question from Brian Bailey. What is the one property or component of steel you find most intriguing and has the most useful or desirable effects for knives and cutting edges, especially where it does not get the interest or attention it deserves? Okay, I think one property is hardness, toughness, balance. So for any steel, as you heat treat it harder, typically the toughness goes down. So here's a chart for high alloy non-stainless steels. You can see as hardness goes up, the toughness goes down. And in knives, we want high hardness and high toughness because we want thin cutting edges. Thin cutting edges with acute angles cut better and cut longer than more obtuse or thicker edges. But to have a thin edge, it needs to be both hard and tough so that it can resist both deformation and chipping. And so it's very difficult to get both of these properties at the same time. To add extra elements to the equation, when you have a high wear-resistant steel, typically the toughness is lower. So if you want to have a steel that is both very hard and very tough and very wear-resistant, it is difficult and or impossible. So for any steel, even high-toughness steels, as they get harder, the toughness goes down, and you can see that they sort of get tighter and tighter bunched together at higher hardness. Where Venatus 4 Extra at 64.5 Rockwell can be, 12 or 13 foot-pounds, not nearly to the point of its 20 foot-pounds at lower hardness. And then these high hardness steels, they just are all together the same. However, there are still differences. You can see CPM T15 or 10V are significantly tougher than 15V, for example. And even Rex 76 is tougher at 67 Rockwell than Maximet or Rex 121. And these can be substantial differences. Dropping a knife on the ground, it'll snap if it's Rex 121 and maybe not if it's Rex 76. So trying to get steels that are balanced, where they have good wear resistance but good enough toughness where they are still usable at high hardness, is important. And this was one of the things I was looking for with MagnaCut, that it would be balanced where it could be used at high hardness if desired to give thin edges where you want, because a thin edge cuts longer. If you go to a more acute edge angle, that has a much bigger impact on your edge retention than the wear resistance. So having a balanced steel can lead to better edge retention if it has the appropriate geometry. And that's one of the reasons why I made MagnaCut the way that I did. Next question. Why is there no equivalent of the CATRA test for cooking knives where abrasion resistance is not much of a consideration? Okay, so the CATRA test is a slicing edge retention test. It's primarily controlled by abrasive wear resistance, as Robert said. However, I don't know if it has no effect on cooking knives. I've seen many claims from many kitchen knife enthusiasts where they have said that they're more wear-resistant steels cut longer in the kitchen, and I have noticed this as well. There can be complicating factors like higher hardness versus lower hardness, but often people will compare their white steel knives at pretty high hardness to higher wear resistance steels at similar hardness, and many people will say that their high wear resistance steels cut longer. But why is there no equivalent for cooking knives? Well, if we're not talking about abrasion resistance, we're talking about some other failure mode. So we were discussing strength and hardness to resist deformation. We were talking about toughness to resist chipping, or we can add in corrosion resistance because in the kitchen we can be cutting acidic foods, which can lead to corrosion of the edge and loss of sharpness. I did a study on this a long time ago where I dipped knives in lemon juice and then measured the sharpness after, and the sharpness would go down with exposure to lemon juice. So to have an equivalent for cooking knives, you'd have to be measuring one or more of those properties. So CATRA is just abrasion resistance. Hardness is just a measure of strength or hardness. The impact test is just a test of impact toughness. And when we do what are called real-world tests, typically we're combining those properties in some way that's supposed to represent real-world use. But that is difficult to do because a thinner edge is going to behave differently than a thicker edge. So what would be your standard procedure? You know, would you whack a knife into a cutting board a bunch of times to have a combination of strength and toughness or something? You know, people can come up with these kinds of tests. Or you can look for steels that have the highest hardness toughness balance like we were discussing before. If abrasion resistance really doesn't matter, then you want maximum hardness and maximum toughness. And maybe there's some balance there. So those are things you could look at, Robert. Stacy asks, does bainite have a place in knives? So I have talked about bainite before. What is bainite? Do I have a good chart here? Well, to talk about the potential benefits of bainite, this is quench and tempered, meaning normal martensite, you heat it up hot, you quench it in oil, then you temper it at a low temperature versus an Austemper. And this old chart shown in a bunch of old handbooks that I recreated here, 53 Rockwell C1095, the Austempered, that means bainite, was way tougher than the quench and tempered. So bainite, very attractive. So what they do with bainite is instead of quenching and then tempering, they quench to an intermediate temperature like 400, 500, 600 degrees Fahrenheit and then hold it there for some long period of time, and it forms a phase called bainite, which looks sort of like tempered martensite, but it has somewhat different properties. And I have recreated some of these old tests. So here is a chart of O1. So these are all quench and tempered down here. And you can see that I maxed out around 15 foot-pounds with O1 when I used a relatively low austenitizing temperature of 1425 and tempered at 400. That gave me around 58.5 Rockwell. However, with the same Austempering treatment, I got over 20 foot-pounds. So a benefit of Austempering can be high toughness at sort of intermediate hardness levels. The reason why it does this is because martensite has an issue called tempered martensite embrittlement. So this is L6 tool steel, and you can see if you increase the tempering temperature, the toughness goes up, but then when you increase the tempering temperature to 500 degrees, the toughness actually went down. And the hardness would also be going down. So looking at the data sheet for L6, so 64 Rockwell, 15 foot-pounds, 61 Rockwell, 43 foot-pounds, but then 59 Rockwell, 38 foot-pounds. So the hardness went down and the toughness went down, which we don't want. You know, so it'd be better to temper at 400. But what if you want to have something in the 59 Rockwell range with improved toughness? Well, a good way of doing that is to use an Austemper. So we would hold the steel at some intermediate temperature above martensite and get in that 58, 59 Rockwell range. To have one more example, I did the same thing with 50 to 100. So 50 to 100, I got quite high toughness in the range of 57 to 59 Rockwell by tempering from 400 to 500 degrees Fahrenheit. But if I austenitized hotter to get higher hardness with 1625, then the hardness got higher, but then it looks very similar to the hardness-toughness balance of normal quench and temper. So tempering can be useful for intermediate hardness ranges, let's say for axes or really large knives. But for thin cutting knives, quench and temper is usually the way to go. Okay, question from Alfredo. Austenitizing soaking time. How to determine minimum, maximum, effect on steel, etc. Okay, so austenitizing. There's a couple of things we do during austenitizing. Austenitizing is the step where we heat to high temperature prior to quenching, such as in oil or in air. It depends on the steel. So the main things we want to do are soak the steel throughout. So, if it's cold in the middle, it has been insufficiently soaked. That is relatively obvious, I think. The other things we want to happen are the transformation in the steel. So the steel has to transform from magnetic ferrite to the non-magnetic austenite before you quench. And we also need to dissolve enough carbide to get carbon and other alloying elements in solution prior to quenching. Carbon is the element that gives us the hardness that we need, so it needs to have enough carbon in solution prior to quenching. We lock in that carbon, and it makes really hard martensite. The more carbon in the martensite, the harder it is. So this is a chart for 50 to 100 where they simulated carbon and chromium in solution versus austenitizing time. You can see that at the beginning, the change in carbon is very steep, and then it flattens out with enough time. And so if you get above this 10-minute line, then we're in a very flat region. And so even if you are off by 10 seconds one direction or another, or using a thicker piece of steel, if we just use 15 minutes or so, we'd be in this flat region. And even with different knives or the steel heating up at a different rate, blah, 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 it's going to be pretty flat in terms of properties. Where some knife makers try to do very short hold times, like 5 minutes or even less, and then they can have a lot of variability in their process, especially when they're looking at different sizes of knives and other things like that. So I usually recommend using longer hold times, and if you need to, you can drop the temperature by a little bit. Temperature matters more than time, but if you're holding for longer at the austenitizing temperature, you can austenitize 5, 10, 15 degrees colder to compensate, but typically that's not necessary. Another reason to avoid very short austenitizing times, this is a study we did on 8670. When we held for 5 minutes, we got 59 Rockwell and 12 foot-pounds. But when we held for 10 to 15 minutes, we got 60 Rockwell and 15 foot-pounds. You can see the toughness didn't really change between 10 and 15 minutes. So knife makers are very worried about grain growth often. They want to have a very short hold time to avoid grain growth. But as I mentioned, temperature matters more than time, and under austenitizing is also detrimental. You can see we had both lower hardness and lower toughness. So don't be afraid of soaking. Soak your steel like it says on the data sheet. The data sheet usually gives a recommended austenitizing time. Sometimes it even changes the austenitizing time based on the temperature you choose, because the hotter you go, the shorter the necessary hold time. But my general recommendation, don't be afraid of soak time. Make sure you're soaking long enough. Usually over soaking is not as likely as under soaking, especially with the types of soaking times that knife makers are using in the 10 or 15 minute range. Okay, one more question. I'd love to learn more about the mechanisms involved in reduction of stainless properties at the higher tempering temperatures of some stainless steels. What temperature does that start to occur? What causes it, etc.? Okay, here is the VanX steel datasheet, and you can see that as we temper hotter, this is 200 degrees Celsius, it would go up even a little higher in hardness with a lower tempering temperature. And then it goes down in hardness as we temper hotter and hotter. And then it starts to go up in hardness again, and then peaks around 500 Celsius or 950 Fahrenheit, something like that, before it drops down again. So what happens is that we get alloy carbides that precipitate. They're really tiny carbides that look like this. Really, really tiny carbides. You wouldn't even see them with optical microscopy. And they're so tiny that they increase the hardness of the steel. And at the high temperature range, you get alloy carbides that precipitate. At low temperature, you get carbide precipitation as well, but it's iron carbide. At high temperature, you get chromium, molybdenum, vanadium carbides that form. And if you are losing chromium in solution and forming carbides, that is less chromium to form your protective chromium oxide layer, because what makes stainless steel stainless is chromium oxide at the surface. And if the chromium is already tied up with carbon, then it can't form with oxygen to form your protective chromium oxide passive layer. And you can also see here it actually says low corrosion resistance in that range for Vanax. I have done this experiment myself with Vanax. So the one on the left was tempered at 400 degrees Fahrenheit. The one on the right was tempered at 1,000 degrees Fahrenheit. And when I sprayed it with 1% salt water, the 1,000 degree Fahrenheit one got rust spots on it, which it performs more like a normal stainless tool steel, you know, something like S30V, which shows similar behavior. So you can take your Vanax and go from super corrosion resistance to low corrosion resistance by tempering in that range. But this tempering practice is actually quite common. It helps with knife companies when they want to put coatings on the steel that require higher temperatures, like 500 degrees, 600 degrees to put on there. The other thing is, if you've tempered at 1,000 degrees, the steel is less prone to overheating. So when they're grinding and sharpening and things, they're heating up the edge of the steel, and that can temper it to lower hardness. But if it's already been tempered at 1,000 degrees, they can heat up the steel about to 1,000 degrees without affecting the heat treatment. So this can be quite common to temper in this range. I don't normally recommend it, because it can also reduce toughness along with corrosion resistance. This is Z-ware or CPM CruWare tempered at 1,000 degrees versus 400 degrees, and the 400 degree tempering led to a higher hardness toughness balance. I guess the theme of this Q&A is hardness toughness balance. So 400 degrees tempering led to a better hardness toughness balance. Similar with 10V, these are the 1,000 degree tempers down here, where we got like between 4 and 5 foot-pounds. And we tempered between 400 and 500 degrees, we got around 7 to 8 foot-pounds. So a significant improvement in toughness at the same hardness. So a reduction in corrosion resistance, a small reduction in toughness. I prefer tempering in the low temperature regime rather than the high temperature regime. Okay, I think that's all the questions I can answer right now before my throat dies. But thanks everybody for watching. I hope you learned something. Bye-bye.